All right, so we are going to discuss today equilibrium. Now, if I had told you equilibrium prior to this chapter, what does that bring up? What equation, what situation does that deal with? That is correct. So that would be? There it is. That is Newton's first law is the law of equilibrium. All the forces going forward, backward, up, down are equal. And how would you know when something is following equilibrium? No, not quite.
Oh, sorry, not changing.
Very good, yes. Now, a lot of times that is your best bet, obviously, but no, it just means that it's not what? Accelerating. Okay, so we need to add another piece to that, okay? So we have sum of forces equals 0, and we're going to just give another, kind of similar to what we did last chapter. This is not equilibrium, but we've got almost another equilibrium we need to discuss. So we're going to call this guy translational equilibrium. So still equilibrium like it was, but we need to add something else. The other day I gave you an example where we talked about shoving Spanauer with a force that would cause torque or not cause torque. The example, of course, real quickly, here's Spanauer from a top-down view, his hands, his head, there we go. And you come by, if you shove him right there, does it cause torque? Yes, yes, no, yes. No, it doesn't. Why did it not cause torque? So there's no lever arm is what I'm looking for. Very good. Then the second circumstance that we looked at is I said, all right, here's Spanauer, and you come over here and you shove him this way. Does that cause torque? No. Absolutely not. Is there a lever arm? Yes, there is. Why doesn't it cause torque? Parallel or not perpendicular, either one is fine. Next. Okay, I said, of course, what if you came over here and you shoved Spanauer at the side in that direction? Should that cause torque? We did a demonstration. Mina came up and shoved me, and we saw, yes, in fact, I rotated as you would have expected me to do. The final example, though, was this. If Mina comes up and shoves me on that shoulder and that shoulder at the same time, careful of this next part, does one of those forces cause torque? Yes, it does. Do both of them cause torque? No. Yes, them do both cause torque. So the following question is, did Spanauer rotate? No. Why not? Oh, not quite, not what I'm looking for. What did the torques do to each other? They canceled each other out. So is it torque by itself that decides rotation? No. See the trend coming. What is it that decides whether or not something rotates? The sum of torques. So if sum of torques, like in the example with shoving Spanauer, are equal to 0, then if you had to guess, put a word up there, what would you guess the name is of that situation? There it is. So equilibrium by itself, just as a singular word, by the way, is still in effect. It is simply this. Equilibrium does not mean just one thing anymore. It means both of these things are true. We didn't have to worry about this prior to this particular chapter because when you did a force diagram, where were all forces drawn from? Center. So did any of them cause torque? So arguably, without realizing it, everything was in rotational equilibrium because there were no torques. Now that we are in this chapter, we do have to worry about both of them at the same time. Is it possible to get one without the other? Yes, let's start with the easy one. What situation would be one in which you have rotational equilibrium, but not translational equilibrium? Remember that you've never had you've always had rotational equilibrium up to this point, so you're really just looking for a situation when you don't have translational equilibrium. What does that look like?
A car hitting the gas.
Car hitting the gas, or literally any object. What's the word? Accelerating. Right. There it was right there. I was in rotational equilibrium, but I was not in, and arguably actually last chapter, you got to see the opposite. Okay? Is this in translational equilibrium right now? Yes. Okay, careful with this next one. Be really careful. Is this in rotational equilibrium right now? Yes, it is. How come? Well, let's do this real quick. When do you know when it's not in translational equilibrium? It's accelerating. So when do you know it's not in rotational equilibrium?
When it's staying constant. Angular acceleration.
When it's angularly accelerating. I say that to then say, can you move and still have translational equilibrium?
Yeah.
Yes, if you go at a constant velocity. Now, obviously, as you mentioned before, the easiest thing is to have it not moving. You can see it, cool. But bringing this back up, is this in rotational equilibrium?
Yes.
Yes, it is, because it is a constant. So when would it be not in rotational equilibrium? Okay. So that is good to know all of those things, but just so you know, what we're going to transition into now are what are known as bridge problems. This chapter has, we kind of hit it fairly shallow in all of the topics. Certainly there's a lot more depth that you can go into, and if some of you decide to go forward into engineering and sciences, you will go a lot further. As a matter of fact, torque, if you decide to be a civil engineer, I want to say like 80-90% of your college homework are going to be torque problems in a nutshell. It's ridiculous how many of those deal with that. Okay, you go a lot further. So do take that in mind. Okay, do we expect you to perfectly understand everything in this chapter? No, there's a lot more depth that you can get out of this. But to help you out, what I'm going to do is I'm just going to basically name like a type of problem that you're regularly going to see. This is kind of similar to what I did when I did all the way back in 2D kinematics, and I kept calling them rally car problems. The purpose of that is to be like, hey, these operate the exact same way as this one that hopefully you already know how to do. These are called bridge problems. Ultimately, if I wanted to step back from calling them bridge problems, we would call them equilibrium problems. But ultimately what it comes down to is you have a situation where both of these are true, and we get rid of my technical conversation. We say, okay, let's start with a zero velocity, a zero angular velocity, and then both of these are true, right? Technically, both of these could be true and not, but I'm imagining that when you guys are going down the interstate that you are not dealing with what I'll call a Mario bridge, right? Where the bridge is in fact in rotational equilibrium and rotating around regularly as you try to drive by down the interstate and just time it perfectly. It's harder to get extra lives here in real life. So, yes, we'll go ahead and assume that it's not moving to begin with. All right, now I'm going to do something here in class. It's not going to translate well, so I'm going to hit pause. I have clicked the button. We're starting. All right, so like I said, we are going to be using this in the form of bridge problems. Okay, for people online, I will draw this here in just a second, but for you guys in person, humor me with this real quick. Let's do much simpler than the example I just gave. Well, I'll leave this up because it's cool. All right, here we go. I have a meter stick setting on two pillars. This one's sitting at 30 centimeters and 90. You don't have to get exact numbers, and the marker is sitting at 70. Humor me with an extended force diagram of that situation right there while I draw that rough situation for people online. By the way, when you draw this, even though it is a sizable pillar, what I would probably suggest that you do is, in your pictures, I would probably suggest that you draw something like triangles, so you only see it hitting at one location, okay? Totally up to you on how you want to do that, but I would suggest that. Now, technically, by the way, there are multiple of the same type of force here. What is there multiple of? Normal. As a matter of fact, there's actually, out of the 4 forces you should currently be drawing, 3 of them are technically a normal-esque type deal. So I'll tell you specifically as regards to the pillars, when you label these, there's a lot of ways to do this, but the 2 I have found the easiest, and I'll let you use whichever one you guys find to be the easiest, is either left and right, or usually 1 and 2. You can subscript them however the heck you want, but since they are usually different, we do need to make sure that we know they're different amounts. Which would you prefer, 1 and 2 or left and right? I heard both. I heard more 1 and 2. Okay. Personally, you can do whatever the heck you want on the homework. I don't care. I heard more 1 and 2, so in class, I'm going to use 1 and 2 as well, knowing that they're actually normal. All right, so that being said, where do 1 and 2 go?
On the triangle.
Okay, on the triangles. Actually, let me draw, where did the marker go? The marker's like over here. So based on where I drew the marker, tell me this. Which one should be bigger, force 1 or force 2? Force 1 should probably be bigger, yeah. Let's go ahead and actually Now, if you don't draw that perfectly on your homework, I really don't care. Okay? It's helpful to take a few seconds to try to think about that a little bit more, but not imperative to solve the problem. Now, let's start to do this because this next conversation is important, and I just want to have it once so that we don't have to keep having it, okay, on what certain things are. Let's talk about gravity. Some people might look at this situation and go, oh, there's two gravities up there. No, there isn't, because of the following. When we draw an extended force diagram, well, you look on, those of you people in person, sorry, people not in person, okay, you see four objects, yes? Which object are we actually drawing the extended force diagram on? The bridge. And that's what we're always going to be drawing on, not on anything else. So technically, what is the only gravity there? The one on the bridge. Where does it go? Center geometrically. So somewhere right about here, not in the center of the two pillars. Yes? That's force of gravity. Now let's talk about this guy over here. What did you name it? Let's knock out the easy stuff first.
BM. Yeah, I also did that.
What would you call BM?
Bridge marker.
Oh, careful. Because it would be, in this case, it would actually be backwards. But wait a second. Okay. Oh, that's why I wanted to be careful here. And that's why it's important. That's why it's ridiculously important that you remember what the extended force diagram is on. Since it's on the bridge, which way does the force go? This force goes down, not up, but I want to talk about that real quick for a couple of reasons that will help you long term. Okay? I'll tell you long term, I'm probably just going to call this, like, past this particular point, I'm usually going to call this force of marker. But let's go ahead for right now and call it marker on bridge. I'll explain why here in just a second. You do not usually have to draw a separate force diagram past this point, but let's go ahead and draw the marker over here and have a brief discussion of not an extended force diagram, just a normal force diagram on this marker. As the marker is sitting there, what is its force diagram? And instead of normal, let's replace it with the corresponding
Bridge marker.
Correct. How do you know they are equal? Correct. This is important. Since it's not accelerating, technically this marker is following which law? Okay, so watch here. Is this force technically gravity?
No, the gravity.
What technically means no. No, it's not. What is this force actually? No, that's not. Right, so what is that actually? Fundamental forces. Right? So what is that fundamental force-wise? It's electromagnetism, which is technically what? No. What is electromagnetism going all the way back? It's the attraction or repulsion between positives and negatives. Specifically what that actually is there's electrons on the outside of the marker, there's electrons on the outside of the bridge/ruler, and what do they do to each other? They shove each other away. Now, I say all this technically. I want you to know what it is. This conversation will absolutely come up in the homework, but also I'm going to let you know that I'm going to retreat back and say later that you can actually use gravity because here's why. So, again, here we go. Is that actually gravity? Technically.
Yeah. Wait, no.
Technically, is that gravity? No, that's the electrons here pushing down. Awesome. Now, are these two equal?
Yeah.
Because of which law? First. Are these two equal? Yes, because of which law? Third. So, is that technically gravity? No. Based on what we literally just proved, is it equal to gravity or mg? Yes. So past this particular point, here's what you got to know. That's not gravity, but I can calculate it with mg. Everyone cool with that? The counter to that would be this, okay? Imagine this marker was like an actual living thing that could put force and go over there. What would that marker do that this would not be the case, they would not be equal? Yeah, literally it's you getting on the scale. You get on the scale and you bounce up and down. Is your actual weight changing? You should be following along. No, your weight's not actually changing, but is that number on there changing?
Yeah.
Yes, because the force of the scale is changing because you are accelerating. So if the marker did bounce up and down, and I could draw this in an animation, what about this would change? this amount would go up and down, up and down, up and down. So would that number go up and down, up and down, up and down? Which makes sense, because if you were on a bridge with somebody and wanted to scare the crap out of them, to thinking that the bridge was going to possibly break, what do? You bounce up and down, up and down, up and down, changing the amount of force that you put on the bridge and scaring them into think that the bridge is going to break, and if it actually is too much, then it does break and you die. But we're not worried about that, okay? Anyway, so past this particular point, just use that with MG, even though it's not. Conversation over, so we don't have to have that conversation again. Everybody cool with that? Cool. Let's do some math. We're going to do another bridge problem here, but I'm going to make some of the numbers a little bit easier so you can try to focus on how these things get put together. But ultimately, it's the same type of thing.
No, it's not for me.
Hello? Yeah, she's right here. All right. All right, so here's the problem. We're gonna have a person we're gonna have a bunny rabbit walk up to like a stream and walk across a couple of 2x4s to get from one side of the river to the other side of the river. Everyone cool with this? Well, I don't know. Someone set them down earlier, and so they're sitting there. I don't know. The bunny doesn't care, but there's 2x4s sitting across. Anyway, who cares? All right, so we got a rock on one side of the river, and then there's some 2x4s stretched across to another rock. Okay, roughly how big are 2x4s? Lengthwise. 10 feet. Wait, no, 8. Thank you. 8 feet. So I'll round it on meters. Let's go about, let's say 2.8-ish meters. Okay, and we're going to put a bunny up here. Where do you want the bunny to go? Not the middle, not the sides.
In the air, then.
No, it's got to go somewhere on the bridge. I mean, it's not going to go directly in the middle. It's not
1 meter from the left.
1 meter from the left. All right, so the bunny is going to go across the.
I thought those were bunnies.
All right, I'm sorry. Let's change this. You guys seen Donnie Darko?
No.
This is a bunny. Okay, and if you haven't seen Donnie Darko, it's the full-grown male in a bunny costume, super creepily crossing the bridge. All right, I don't know why I care about this, but some of you fall asleep, so I got to add details to make it a little interesting. Here we go. What is the mass of the bunny? Remember, it's full-grown male. What?
It's a full-grown man.
Not Jesus. It's not Jesus. He would just walk across.
80.
What's that?
180 kilograms.
Holy
80.
crap!
80.
No, he's not up walking around then. What's the difference? Let's go 80. The mass of the bunny is 80 kilograms. All right, you guys said that the bunny is roughly a meter from the left side. Cool. And roughly, humor me real quick with this and listen carefully to it. How much would, let's say it's 2 or 3 2x4s. How much would they weigh in total? How much do a couple of few 2x4s weigh in total? Make a guess. Like 10, 12 pounds. All right, so cool. So let's say 12 pounds. Which is what? What variable is that?
No, I'm in a kilogram.
No, it's not. That's not the mass.
No, that's not 2 by 4.
Thank you very much.
You did something right.
Cool. How about that energy? All right, next. So here's a bridge problem. Here's the common question that's going to be asked on the bridge problem. It'll tell you all this information, usually mathematically. Again, that's 2.8 meters in total from side to side. 1 meter is what you decided from the left. We decided 80 because some people were a little bit more accurate, but not quite a full-grown adult, and some people were not terribly accurate. All right, and then we got force of gravity of this pretty close to about 12 pounds. And the reason why I was a little bit difficult on giving you what units I gave you is because often this is what problems are going to do, just based on what is easy access information to be able to do this. So we got to learn how to treat both numbers. Now, the question in this particular case is how much force does each rock put out? So in other words, what we're trying to find is what is force 1 and what is force 2. Here's the setup of the problem. What should you probably do next? Extended force diagram. I like it. All right. So what goes where? Force gravity goes in the middle, okay? Both middle of it and actually geometric middle. There we go. We got force gravity. What else?
Normal on both the rocks.
And so I think we've been using 1 and 2, right? If you had to guess, which one probably would be bigger in this case, 1 or 2? 1. I think you're probably right. But we'll find out mathematically later. Here's force 1, here's force 2, and what else we got? Force of bunny going which way? Down in this particular case right here. All right. Now our setup is exactly the same. If you got a bridge problem, you got an equilibrium problem. If you got an equilibrium problem here, how do you start? Well, you have these two pieces of information. Let's start with what we know, because maybe it works. Okay? We try to sum the forces into 0. Now, I'm sorry, I try to sum the forces, which are equal to 0 because it's balanced. And I look up here, and even though this is an extended force diagram, it is the same as a normal force diagram. We got forces up, we got forces down, so arguably it's kind of easy. I don't even have to worry about x and y. I could just worry about the y. Yes? Sum the forces in the y. No problems whatsoever except yes. Yes, there is. What's the issue with trying to find force 1 and force 2 by summing the forces in the y? So mathematically, what's the issue with trying to solve here? You have 2 unknowns. And how do you solve something if there's 2 unknowns? Now, just as a heads up, by the way, before you freak out, yes, I wanted the answer to that, but no, that's not how we're going to solve this. If you were like, oh crap, multiple equations, multiple unknowns, that is the answer. We'll worry more about that later, don't worry. But it means we cannot easily currently use sum of forces, yes? But this is an equilibrium problem, which means not only are sum of forces equal to 0, but torque is also equal to 0. Okay. Now, in order to start a torque problem, you would need to calculate individual torques. What is our equation for individual torques?
Force times lever arm.
And we usually use lever arm first. Lever arm times force times sine theta, yes? Now, we could probably we don't want that energy. All right, so we could probably calculate the force, but what's the issue right now with attempting to solve for the lever arms here? What do we need to know first? We got to know the fulcrum. Now, luckily / unluckily, based on what we said earlier, who decides where the fulcrum goes? You do. Now, that is both. Okay, hold on a second. Okay? This is why it's lucky, because ultimately what we said earlier is you could get a second equation with 2 unknowns. And then you'd have 2 equations with 2 unknowns, and you could solve this, except we don't want to do that. So what could you do with choosing where the fulcrum goes so that you don't have 2 unknowns?
You eliminate one of them.
Eliminate what about them? Careful, because I want to be clear for this. I know. What you cannot eliminate a force. You can't. Correct.
Ian, you're so smart.
If you place the fulcrum, let's go green here, at where one of them's at, what gets eliminated? Not force. You can't count. You can eliminate a torque though, because that then will not have a lever arm. Okay, so technically you can put this wherever the heck you want, but where are probably the 2 best options? Either on 1 or on 2. Either one is fine. It doesn't matter. Both will work just fine. I'll tell you probably the easier one is putting it on F1, so let's go ahead and put it on F2. All right. It doesn't change it that much. Humor me. All right. Now, shh, guys. We can lose the forest for the trees. Yes, I understand this is not the easiest thing in the world, but yes, I think you can follow it, and you're going to follow it better if we stop and start focusing. Okay, so we put the fulcrum over here, and now what we do is the exact same thing we regularly do when starting summing the forces. Okay, except now we're going to say I'm going to sum the torques. Usually we'd say sum of forces equal to ma. Right now we can just say sum of torques is equal to 0. So what do we usually do now with sum of forces? We usually start kind of putting them, is it there, and in what direction is it going? And then I'd usually add something about x and y, but we don't have to do that here. So just, is it there, and which way is it going? This is actually why I chose to put the fulcrum where it is. Let's start with F1. Is F1 going to cause torque? 100% positive or negative? Negative, so you're going to write negative torque of 1. Next, going to the next force. Is force of bunny going to cause torque?
Yeah.
Positive or negative? Positive. Is torque of gravity going to cause torque?
Yeah.
Positive or negative?
Positive.
And finally, is torque of 2 going to cause torque?
No.
You have 2 options on this. I'll tell you what I usually suggest. The first option is you can write down torque 2 and then just show that it cancels. The reason it cancels, of course, is because this R right here is 0. okay? But my personal preference, what I would usually do is just not write it because it's not writing torque. I don't care in this particular case. And then just say, okay, these three equal 0. Now, the next step in this particular process is to just go from the big picture torques to how do we calculate all of them individually. If you'll remember, this is utterly similar to when we did sum of works is equal to change in kinetic energy. And we would put out work of gravity, work of normal, work of friction, and then we would break them down individually into their force times displacement times cosine theta. You're going to put that out. That being said, there can be, if you're very clever with this, a way to make this go a little bit faster. I know what I'm looking for is force 1, yes? So what I'm going to do is I'm going to do a little bit of algebra ahead of time by moving this over so I don't have to move it when there's more variables. And what's nice about that is it also shows me something really cool conceptually, and it's simply this. Hey, everything forcing this system to rotate counterclockwise better be equal to everything in this system forcing it to go clockwise, because otherwise it would not be in equilibrium. Make sense? Okay. Then what I'm going to do is I'm going to start filling these out individually. Once again, what's the equation for a torque? Now, all of these have different lever arms and different forces, so be careful with your subscripts. So watch here carefully. We would go lever arm of bunny times force of bunny. And to make your life a little easier, watch me here. What would technically go next? Okay, now watch this, but don't write this so I can show you what to do to make your life easier. Sine theta of bunny. But if you look up here, what is the angle going to be for force to bunny? So force to lever arm. Well, here's my lever arm. Here's my force. So 90 degrees. And what is the sine of 90 degrees? 1. So what I would suggest you do in this case where it's 90 degrees, I want you to remember that sine theta is there. And I promise you, if you just write R and F, you won't. So here's what you do. You just write R and F times 1. Yes, I know mathematically you don't need it there. What is it doing? It's placeholding so that I remember it's only 1 because it's 90 degrees. Make sense? I continue on to gravity. I go lever arm of gravity times force of gravity. I look at the angle. What's the angle between gravity and the lever arm? 90. So once again, I multiply it times 1. That's equal to lever arm to 1, force of 1 times, once again, the angle on that is going to be, I believe, 90. Let's check. Yep, there it is, 90 degrees. You'll notice, by the way, it doesn't matter where the heck the 90 degrees is. It's going to be 90 no matter where I measure it from. So that's times 1. Beyond this point, I don't need you to hold the 1 around. You can just do this mathematically. As a matter of fact, we're looking for F1. This is super easy algebra. What's the only thing I need to do here? Yeah, let's go ahead and just divide by the lever arm. And here's essentially what this says. Watch carefully. If I take all the torque, if I calculate all the torque that this is causing spinning-wise, then all I have to do is that's got to be the same as the torque this thing provides. And if I divide by this thing's lever arm, that tells me how much force is necessary to cause that much torque at that lever arm so that they are balanced. That's essentially what I just found. All right. Now, a couple things we should have done ahead of time. Let's knock out real quick. Okay. How do I get both of these in the terms of force? Well, for starters, back to bunny. Is this actually gravity? No. Can I use mg and still calculate it correctly? Yeah. Cool. So the force of bunny is simply going to be mass of bunny times g, or 80 kilograms times g, which should be like, what, 700 and change? I'm not sure. Someone calculate that. Okay. Sadly, we were given this in pounds. So what do we have to do to get this? What units do they need to be in? Newtons. So what do we need to do for this guy? Yeah, just go ahead and convert. So write 1 pound is equal to 4.45 newtons. All right. What do we got here? That should be 44.5 plus another, what, 8.9. So 40, 52, 53.3. What is it?
53.4.
Ah, I was off. What a terrible science teacher. All right, and then 80 times 9.8 should be close to 800, so let's go 790-ish. 784. Okay, so coming down here, those aren't too hard. Let's go over here. Do be careful with your lever arms and remember what the definition is. What is the definition of lever arm? From where to where?
Fulcrum.
Fulcrum, center of mass. So I did give you a tricky one. This is arguably why it's tricky. It's not that tricky. Okay, what should the lever arm for Bunny be? 1.8. The total is 2.8. That's 1. So we know that that should be 1.8. So we should have 1.8 meters times the 784 Newton bunny, plus what should the lever arm of gravity be? 1.4. Very good. Times the force of gravity, which was our, 53.4 newtons. And what should the lever arm for the F1 2.8 is correct. Honestly, if you followed all that, that's all the more difficult. Well, not all the more difficult, but 80-90% of the way there on this. All right, what'd you get?
530.7 newtons.
Sounds about right. Can I get a couple can confirms? Yes, cool beans. All right. More good news, bad news time. Let's start with bad news. What did I ask you for?
1 and 2.
Sorry, I have 1 and 2, and we've just covered 1. So there are 2 ways to solve for 2. Okay, I'm going to tell them to you because I know the first thing I'm going to tell you, like, that's not easier. I'm not doing that. Okay, but there will be a time that definitely is easier in this chapter. The first thing that you can do is you can remember that we solved for F1 by placing the fulcrum here. So what's the first thing that you could do to find F2? Not even just that, yes, that too. You can literally move the fulcrum anywhere now, right? Because yes, we put it here so it would cancel F2. Why don't we have to put it on F1 anymore? We now know what F1 is. You could put the fulcrum in the middle and all this would work just fine as well. Obviously, that's not the easiest bet. Even if I did that, that's not the easiest regardless. Here is the easiest thing, but it's not always the easiest thing for later. At the very beginning of this problem, I told you that let's start looking at the situation for summing the forces because, hey, we know how that works. But why couldn't we do it? So why can we do it now? The only thing I want to remind you about summing the forces is that we've been talking about positive and negative torques. How do you deal with positive and negative forces? Same way we always have, just up and down. Also, we talked about the fact that torques cancel. Do forces ever cancel? They do not deal with fulcrums. Forces do not cancel. You do have to deal with all of them. So here's what it would look like at the very end if you did it what I would consider the easiest way. You would say sum the forces. If you want to say y, awesome. Technically it is the y. Equals mass times acceleration in the y, but yeah, we know it's equal to 0. And this would be force of 1 positive because it's up, plus force of 2 positive because it's up, minus force gravity negative because it's down, minus force of bunny equals 0. What does that equation say? Simply put, hey, all the forces pushing up should equal all the forces pushing down. That's all it says. So if I take all of the forces pushing down, aka do a little bit of algebra, force of gravity plus force of bunny, this would be everything down, and I subtract what I know force 1 to be, the leftover better be force 2. Yes? So I go over here, force of gravity was that 53.4 newtons, plus the force of bunny being 784 newtons, minus what we literally calculate right here, 530.7 newtons, and how big is the force of 2? It's like 300-ish, isn't it?
306.7.
And does that confirm what we said at the beginning of this? Which one of the 2 of these did we expect to be bigger? And is that in fact what it is? Does this mean, humor me real quick, I'm almost done, I promise. Does this mean as the bunny walks, I don't know, across the bridge, that these numbers all change? Well, sorry, specifically F1 and F2. Yes, they do in fact change as you walk across the bridge, just the same as all the pillars change as you drive across Alton Memorial Bridge. Thank you guys for your attention.